Again, welcome to Statistics. This is DSRT 734 class. In this lectures, we're going to cover the chi-square test, goodness of fit. So again, this is Unit 10 lectures, and our main objective is to cover the goodness of fit. That's using the chi-square distribution to test whether frequency distribution fits a cream distribution. Again, using the chi-square distribution to test whether a frequency distribution fits a cream distribution. In this case, we're going to use the chi-square distribution table. And also using chi-square most of the time when a data is again categorical. So let's start with the lectures. So the first thing we're going to learn here is what is a multinomial experiment. So a multinomial experiment is where we, again, chi-square distribution testing fitting. Because here we can have different categories of outcome of an experiment. So for example, here we say a multinomial experiment is a probability experiment consists of a fixed number of tries in which there are more than 2 possible outcomes for each independent try. Again, we did a binomial experiment. We say binomial experiment, then outcome, the possible outcome for the experiment is 2. That's why it's called binomial, 2 outcome. Now, in a chi-square distribution concept, a multinomial experiment fits in, because in a multinomial experiment, our outcome can be more than 2. Must be more than 2. We can have an outcome of 20, 10, 3, 5, any amount. So in a multinomial experiment, chi-square distribution testing again is used. So again, one more time for the definition. The multinomial experiment, again, the probability experiment consists of fixed number of tries, in which the key word here is in which there are more than 2 possible outcomes for each independent try. And when it's 2 outcomes, we use binomial, or it's a binomial experiment. So that's what we say. A binomial experiment have only 2 possible outcomes. And I think we went through binomial experiment when we covered the probability distribution concept. So a binomial experiment had only 2 possible outcomes. Also, the probability for each outcome is fixed, and each outcome is classified into categories. And again, we're going to see an example soon. So this is the example here. We have a radio station that claims that the distribution of a music preferences for listeners in a broadcast region is as shown below. So this is the claim of the radio station. And the distribution, we said 4% of the listeners are classical music, 36% are country, 11% is gospel, 2% is oldies, 18% is pop, 29% is rock. This is an example of a multinomial experiment, because the possible outcome here again is 6 different types of music preferences. So again, the question here says, radio station claims that the distribution of a music preferences for listeners in a broadcasting region is as shown below. We have 6 different preferences, or I would say in this case, 6 different outcomes. So it's again a multinomial experiment. So here we say that each outcome is classified into categories. And also the probability for each possible outcome is again fixed. It's again fixed. So we move to again the chi-square goodness of fit test. Again, we are going to do an example whereby we use a multinomial again experiment to test a claim, and again using the chi-square distribution testing. So here we go through what is a chi-square goodness of fit test. So a chi-square goodness of fit test is normally used to test whether frequency distribution fits an expected distribution. where the frequency distribution fits an expected distribution. The null hypothesis states that the frequency distribution fits the specified distribution. And then the alternative hypothesis states that the frequency distribution does not fit the specified distribution. So again, this is the concept of, again, chi-square goodness of fit test. The null hypothesis will state that the frequency distribution fits the specified distribution. And the alternative hypothesis states that the frequency distribution does not. And we always know that alternative hypothesis always goes against the null hypothesis. So we have an example here for chi-square goodness of fit test. Here we are going to test the radio station. We saw the radio station is again a multinomial experiment because we have 6 different outcomes or 6 different music preferences. So now we want to test a claim that was made by, again, the executive of the radio station. So the example here says to test the radio station claim, the executive can perform a chi-square goodness of fit test using the following hypothesis. And now here we have the claim was given to us as a multinomial. Now we can see that we have more than 1 or even 2 or even more than 2 outcome. So if I have an HO with 6, in this case is 6, or with 3 or more outcome, I can use t-test or z-test. I can't. The standard normal test, no. So here we are going to use this is the example of chi-square goodness of fit test. First, as we saw, it should be a multinomial experiment test. An example here, we have 6 different outcomes or categories. So our claim for HO says that the distribution of music preferences in the broadcasting region is 4% for classical, 36% for country, 11% for gospel, 2% for oldies, 18% for pop, and 29% for rock. So these are the claim. We can see 1, 2, 3, 4, 5, 6 different categories. Now our HA should go against the HO. So here we say the distribution of music preferences differs from the claim or expected distribution. So we have to go against the claim with HA. So this is a very good example of, again, chi-square goodness of fit test. We can see all the hypothesis testing we did. We never have an HO, a claim that we have 6 different categories of a claim. Our claim here is that if it's, let's say we are using the standard normal distribution or the what we call the Z testing, we should test only one music. We say, okay, 96% of the customer listen to a specific type of music or whatever percentage it is. Then HA will go against the music. That's if it's only one category. But here again, we have 6 different categories of a claim. So that's why, again, we are using the chi-square goodness of fit test. So here we say, okay, the steps is that to calculate the test statistics, first of all, we know in hypothesis testing, the first thing we do is to state our problem. Second, we state our HO and HA. The next step is to do our test statistics. So we have to, if it's a standard normal, T distribution, whatever test it is, we have to find it. After we find it, we compare with the level of significance, which is the alpha. Then based on the level of significance, we can either reject the HO or we will fail to reject the HO claim. The same concept here. So first step we did, we state our HO and HA. Now the next step is to get our test statistics. So to calculate the test statistics for the chi-square goodness of fit test, the observed frequencies and the expected frequencies are used. Now the observed frequency O of a category is the frequency for the category observed in the sample data. So again, to calculate the test statistics in the chi-square goodness of fit test, we always need to get the observed frequencies and also the expected frequencies. Those are the two items that we are going to use. Now, the observed frequency of a category, again, is the frequency for the category observed in the sample data. Now, the expected frequency of a category is the calculated frequency for the category. So to calculate the expected frequency, we normally obtain it assuming that the specified distribution, which is the hypothesized distribution, the expected frequency for the ith category is n times pi. So I can be, maybe we have, in this case, we have 6 categories for the music. We may have expected frequency for classical music will be, let's say that will be number 1. So that will be our E1. Then it will be the sample or the number of tries times the probability of that. And we can see, I think in the classical, we may have probability, let's say 6%. Then it will be again the number of tries, which is the sample size times the probability of it. Again, we are going to do an example soon, so we will see the steps. So this is the example. Here they say we should find the observed and also expected frequency. And our question here is the same question we had previously. So here we have a marketing executive randomly select 500 radio music listeners from the broadcast region and asks each whether he or she prefers classical, country, gospel, oldies, pop, or rock music. So we can see all the 6 categories again. The results are shown at the right. So they gave us the survey result, the number of tries 500, and this is the category. So when we had all this data here, we will get 500. Out of the 500, the sample size, 8 is classical, 210 is country, 72 is gospel, 10 is oldies, 75 is pop, and 125 is rock. Now, this is our question. We are going to find the observed and also the expected frequency for each music. For each music. When we say music, we mean for each category of music here, classical, country. So we're going to find the again observed and expected value. So the observed frequency, we say is the number of radio music listeners naming a particular type of music. So again, this is our data set. The survey result is based on a sample size of, again, 500. So this is our observed, so this is our observed frequency. That's the number of radio music listeners naming a particular type of music. So classical was 8, so that's the observed frequency for classical music. Country was 210, so that's the observed frequency. Gospel was 72, that's its observed frequency. And then the oldies, pop, and rock. So now we want to find the expected frequency. Remember, expected frequency is the one we have to calculate, and also is the sample size times the probability of that very category, or PI, N times PI. So you can see the first 4% will be 0.04 times N. N is 500. We're going to use 500 throughout. That's the N value. So what we change will be the PI, the probability of that category. It's 4% here, 36, 11%, 2%, 18%, and 29%. So we can see 500 times 4% is 0.04. 500 times 36% is 0.36. 500 times gospel is 11%, 0.11. Then 2%, 0.02 times 500. Then 18%, 500 times 0.18. 29%, 500 times 0.29. And that's our result. So again, this is how we calculate observed and expected frequency. From the definition, they say the observed frequency is what is given to us in each category. And we can see it here. Expected frequency is what we have to calculate, which is normally the sample size times the probability of that category, of each category. Here we have 6 categories, so each category has its own probability. So the formula is NPI. N is the sample size, PI will be the probability of that category. So now we are going to write the steps down or go through the steps. So for chi-square goodness of fit test to be used, the following must be true. So the condition said the observed frequency must be obtained by using a random sample. So again, the sample that we are going to collect should be a random sample. Then each expected frequency must be greater than or equal to 5. So we have to check this condition. All the expected frequency, you can see here, all our expected frequency values are greater than 5. Otherwise, we can't use the test. So that's the 2 conditions. Each expected frequency must be greater than or equal to 5. Now we said that if these conditions are satisfied, then the sample distribution for the goodness of fit test is approximated by chi-square distribution with k minus 1 degree of freedom. Now, when we are using the chi-square distribution table, it's almost like the T table. We need the row of degree of freedom, then we go to the column, whatever category. So here we say the approximated by chi-square distribution with k minus 1 degree of freedom, where k is the number of categories. So this is now when we get the observed and also the expected frequencies, now we can find the test statistics. S square is like chi-square. So that will be the sum of observed minus expected all square divided by observed. So the reason why the summation symbol is here is that, for example, in the music, we have 6 categories. So we are going to find each one, the test statistics for each category, then we had it. So it will be, let's say, 0, 1 minus U1 over U1 plus 0, 2 minus U2 over U2 plus up to 6. Again, we're going to see example in a few minutes. So that's the steps for the chi-square goodness of fit. So first we need to identify the claim, and we need to state the null and also the alternative hypothesis. So here we state the HO and HA. Second step, we specify the level of significance. So we identify our alpha. Then the third step, we identify the degrees of freedom. Here, the degree of freedom is always k minus 1. Then we determine the critical value using the chi-square table or chi-square distribution table. Then step 5, we determine the rejection region. Now, when we get the test statistics, we will know if we are in the rejection region area, because we need to find the critical value using the alpha and also degree of freedom. So again, after that, we know we get the critical value. We can differentiate the reject region with the accepted region. So we need to determine rejection region based on the test statistics value. Then after that, we make a decision. Our decision here is 2 options. Either we accepted or reject the claim. Then we interpret the decision in the context of original claim. Now let's see an example. This example will follow all the steps. So here we're going to perform a goodness of fit test. Using the music preference data to perform a chi-square goodness of fit test to test whether the distributions are different. Now we're going to use alpha equal to 0.01. So the distribution of music preferences, we have what is given to us. And this is again the percentage. Then the actual survey result also is given here. We know the total survey is 500. So we have the values for the classical, country, gospel, oldies, pop, and rock. Then our next step, first we state our HO. This is given to us. And this is what the executive of the radio station claim. They say 4% is classical, 36% listeners is country, 11% is gospel, 2% is oldies, 18% is pop, and 29% is rock. And the total sample size together is 500. So if this is the claim, then HA will go against the claim. So HA said the music preferences differs from the claim or expected distribution. Next, we have to specify the alpha value, which is given to us to be, again, 1%, 0.01. Now, since I know this category of our, we have 6 musical categories, we can find the degree of freedom. So in our previous T distribution, degree of freedom normally is the sample size minus 1 or sometimes minus 2 based on the type of distribution we are, T distribution we are doing. But with chi-square, the degree of freedom normally is not the sample size, but rather the number of categories. So that's why we represent it with K. K is the number of categories. Here we have 6 different categories for the music. So our degree of freedom will be 6 minus 1, which gives us 5. Now, based on the alpha value, degree of freedom, we can again construct our rejection region. So we have 0, the critical value is 15.086. And we have our, we get this value based on what? The degree of freedom and the alpha value. So it's almost the same as the T distribution concept. You go to the chi-square distribution table, look at the row 5, because degree of freedom is 5. Go to the column, look for 0.01. The intersection of the two will give you 15.086. So when I know this now, I need to find the test statistics. If the test statistics value is greater than 15.086, then it will be in the blue region. Otherwise, it will be in the brown region. So either reject or accept. So we know the test statistics formula is a 6 different categories. So we're going to find a chi-square, the sum of 0 or O minus E square over E. O again is the observed frequency, E is expected frequency. So we plug in the values. Again, we have 6. So first is 8 minus 20 over 20. Then second is 210 minus 80 over minus 180 over 180. The third one will be 72 minus 55 over 55. So all square. So all this is 10 minus 10 all square over 10. 10 minus 10 all square over 10. Plus the pop is 75 minus 90, expected is 90. All square divided by 90. Plus 125 minus 145, all square divided by 145. So our answer will be 22.713. So now we go to our diagram. So we have 22.713. So we go to our diagram and we can see that 22.713 is in the blue area. So this means we need to reject HO. Always our brown area is accepting the HO and the blue will be rejecting. So our decision here is that there's enough evidence to conclude that the distribution of music preferences differ from the claim distribution. Since we reject the HO, we're going to say that. So this is another example, performing a goodness of fit test. Here we have a manufacturer of M&M's candies claim that the number of different colored candies in bags of dark chocolate M&M is uniformly distributed To test this claim, you randomly select a bag that contains 500 dark chocolate M&Ms. So that will be our sample size, 500. The results are shown in a table on the next slide. We're also going to use the alpha equal to 0.10 to perform the chi-square goodness of fit test to test the claim or expected distribution. And what will be our conclusion? So first, we know the sample is 500 dark chocolate M&Ms. The alpha is 0.10. So we can again do our chi-square, and the category is given by it's in the table here. So this is it. So the color of brown is 80, yellow is 95, red is 88, blue is 83, orange is 76, green is 78. So the claim is that the distribution is uniform. So the expected frequency of the colors are equal. When we have a uniform distribution, it means the expected frequency of the colors, or this time our category is different colors, they should be the same. If it's uniform distribution, it means brown frequency is 80, yellow should be 80, red 80, blue 80, orange should be the same. That's our claim. To find each expected frequency, we divide the sample size by the number of colors. This is the same concept. So for example, here, brown, our observed frequency will be given to us. Then based on the observed frequency, we can find the expected. So N is 500. And here we have 500 divided by 6. Why divided by 6? Because we have 6 categories. So that would be our E. So let's start with our hypothesis testing. So first, the distribution of different colored candy in bags of dark chocolate M&M is uniform, which means all the colors are the same. Our claim, of course, since we say all the colors are the same or uniform distributed, then our alternative hypothesis will be opposite. So distribution of different color candies in the bags is not uniform. So first we know our alpha, and of course we know our degree of freedom because we know the number of categories, the number of colors. The number of colors are 6, so it will be 6 minus 1, which is 5. So if I know the alpha 0.10 and I know the degree of freedom, then I can sketch the reject region. When I look for the chi-square distribution, when the degree of freedom is 5 and alpha is 0.10, I will get 9.236. So this is my critical value. Blue to my right will be rejection, to my left will be accepted. Of acceptance and rejection of HO. So now we do our test statistics, the same concept. Since we have 6 categories, we are going to find 6. So the first one will be 80 minus 83.3 divided by all square divided by 83.3. Plus the next is 95 minus 83.3 all square divided by 83.3. Then red will be 88 minus 83.3 all square divided by 83.3. Then the next one will be 83 minus 83.3 all square divided by 83.3 plus 76 minus 83.3 all square divided by 83.3 plus 78 minus 83.3 all square divided by 83.3. So when we do that, we get 3.016. Now we can see where the 9.236 is, our critical value. So 3.016 will be to the left of 9.236. So this time we are in the accepted region. So we have to accept HO. So here we say fail to reject HO, which means we accept HO based on the chi-square test statistics score. So this is the claim. HO is the claim that they made. Always HA will go against HO. So if HA is uniform, then HA should be not uniform. We know the alpha value. We were able to find degree of freedom because the category is 6 minus 1 alpha. So when I know the alpha value and degree of freedom, I can find the chi-square value, test statistics, and chi-square normally is not a normal distribution. So now I'll find the test statistics, which we did. So when we do the test statistics, we get 3.016, which means we fail to reject HO because in the brown area is to accept HO. So that will be the, again, conclusion for chi-square distribution to test whether frequency distribution fits a claim. So as we said earlier, chi-square is very good when you have more than 2 categories. So the 2 examples we saw, we have 6 categories. So the hypothesis testing, which we say the goodness of fit for chi-square testing, is the same steps as any hypothesis testing we cover so far. In terms of chi-square, first we have to state our HA and HO. Always HA will go against HO. Then we have to identify our alpha value. The degree of freedom will be the number of category minus 1. So when I know the degree of freedom and I know the alpha, I can look for the critical value from the chi-square distribution table. Then I can do the sketching and I can find the rejection region and not accepted region, not rejected or accepted region. So if I know this critical value and I get the graph, then I'm going to find the test statistics, which is normally the sum of observed frequency minus expected frequency or square divided by expected frequency. Now, when I get the value, I'll see the value lies on the rejection area or accepted area. Then based on that, I may make my decision whether we reject or accepted HO. So those are the steps again for chi-square, and wish everybody the best, and thank you for your time.